Let's begin our discussion on binary math. As you recall from Chapter 1, we talked about communication between computers. And here's the example. One computer wants to send the number 7 to another computer. Computers can only send positive and negative impulses to each other. Those positive and negative impulses are represented as zeros and ones, and we call them bits. So here's the question. If one computer can only send positive and negative impulses to another computer, then how can it send the number 7? And the answer is, different combinations of bits represent different values. Then the next question is, which combination of bits represents which value? In other words, how come 5 negative impulses and 3 positive impulses is equal to 7? And this takes us to binary math. In each octet we have 8 bits, and each bit is a placeholder. The first is a placeholder for 1, the next bit is a placeholder for 2, the next is a placeholder for 4, 8, 16, 32, 64, and 128. So if one computer sends 7 negative impulses and a positive impulse, which we represent as 7 zeros and a 1, it's sending the number 1 to another computer, because we simply have 1, 1, but no 2s, no 4s, and no 8s. If one computer sends 6 zeros, a 1 and a 0 to another computer, it's sending the number 2, because we have no 1s, we have a 2, and no 4s. If one computer sends 6 zeros, a 1 and a 1 to another computer, it is sending the number 3 because 1 plus 2 is equal to 3. If one computer sends 5 zeros and 3 1s to another computer, it's sending the number 7 because 1 plus 2 plus 4 is equal to 7. Here's some other examples. A 1 followed by 7 zeros is equal to 128. A 1 followed by 6 zeros and another 1 is 129, because 128 plus 1 is equal to 129. And if all 8 bits are set to 1, then that equals 255, because that's equal to 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128, which adds up to 255. When all 8 bits are equal to 1, that is equal to 255. Communication between computers. Computers can only send positive and negative impulses to each other, which are represented as zeros and ones, and we call them bits. 8 bits together are equal to 1 byte, and different combinations of bits represent different values. That's how 5 negative impulses and 3 positive impulses can equal the number 7. Now let's review what's meant by a packet. A packet is a message which is sent from one computer to the other. It contains the data which is being sent, in this case the number 7, and the header which shows who it's being sent to. In this example, the packet is being sent to workstation 1. Workstation 3 is putting a packet on the wire, and the header indicates that it's going to workstation 1, and the data indicates that we're sending the number 7. Well, this is how we diagram it, but really this is how the computer sees it. This is a diagram of a simplified packet. In this example, the computer sees the header as 7 zeros and a 1, meaning it's going to workstation 1. And the computer sees the data portion of the packet, meaning 5 zeros and 3 1s, as the number 7. So this is a diagram of a simplified packet. Now, let's move on to an IP header, which has a 32-bit address space. A packet has the data and the header. And the header in this example shows the IP address of the destination computer. And since this is an IP address of 129.15.2.1, we can see that these 32 bits represent that IP address. The first octet represents 129. The second octet represents 15. The third octet represents 2. And the fourth octet represents 1. And of course, to the far right here is the data portion. that IP header has a 32-bit address space, meaning 32 bits are used to represent the IP address of the destination computer. Can an octet be 999? Well, IP has a 32-bit address space divided into 4 octets, and they're 8 bits per octet. And if all 8 bits are set to 1, then the total value is 255. So, an octet cannot be 999. Now, let's look at the IP address and subnet mask in decimal and in binary. Now, this is the way we usually look at an IP address and subnet mask. The IP address is 131.15.0.129, and the subnet mask is 255.255.0.0. But here is how the computer sees it. The computer sees it in binary. This string of 32 bits represents the IP address. The first octet is 131. The next octet represents 15. The next octet represents 0. And the last octet represents 129. That's the IP address. This string of 32 bits represents the subnet mask. The subnet mask is 8 ones, which is 255, and another 8 ones, which is 255, and then 8 zeros, which is 0, and another 8 zeros, which is 0. So the subnet mask, if we look at it in binary, in this example, Class B subnet mask is 16 ones and 16 zeros. There are 3 classes of IP addresses, Class A, B, and C. And a Class A address uses a Class A subnet mask of 255.0.0.0. And if we look at it in binary, it's 8 bits followed by 24 zeros. Conversely, a Class C subnet mask is represented as 255.255.255.0. And in binary, that is represented as 24 ones followed by 8 zeros. We can also write that in a shorthand notation of /8, /16, or /24. A Class A subnet mask has 8 bits. And another way to write that is simply /8. It's just a shorthand way of showing a subnet mask of 8 bits. A Class B subnet mask is a 16-bit subnet mask, so we write /16, and a Class C subnet mask is 24 bits, so we rate it as /24. The maximum number of computers that we can have in a Class C network is 254. How come? Because we have only 1 octet that can be used to represent the IP address, and there are 8 bits and an octet. You can get a total of 256 values. But since you can't use all zeros and you can't use all ones, that allows us a total of 254 potential host IDs in a Class C network. Now, conversely, a Class A network allows us to use 3 octets for host ID. So a Class A network has a theoretical maximum of 16 million host IDs because we have 3 octets to use to assign IP address. This is a Class A, a Class B, and a Class C network. In summary, in this section we looked at binary math, and we saw that IP has a 32-bit header. 32 bits are used to represent the IP address. It is divided into 4 octets. Each octet has 8 bits, and each bit in the octet is a placeholder. The first represents 1, the next represents 2, 4, 8, 16, 32, 64, 128, and 128. And that is how 5 zeros and 3 ones can equal 7. And this concludes our section on binary math.